we are talking about 12.3 in this video, which we saw in, in 12.1, we kind of did this idea of expected value and variance of discrete data, a discrete random variable. So now in 12.2, we kind of talked about what it means to have a continuous random variable. So now it's only natural to talk about, well, how do I find expected value and variance for a continuous random variable? And so you saw, I'm not going to state this definition super formally, but we do want x, right, to be, let's let x be really not formally here, a continuous random variable, where that's different than discrete. And it can take on values between, let's say, a and b, capital A and B. And then let's let little f of x be this random variable's probability density function, which is what we talked about in 12.2. Okay, then how do we define, and you saw this in the book, but how do we define expected value? So then expected value, so remember our expected value before for discrete random variables was just the relative frequency, right, times the actual outcome. So our expected value then, we call E, of course, of our continuous random variable. If I want to know my expected value between A and B, I'm going to just integrate from A to B. And this is going to be kind of similar to what we had for discrete, except what that integral does for us is it allows us to do this over an interval and consider all possible options between A and B, not just discrete or specific values, right? That's what an integral does for us. So this kind of makes sense. If you remember, our expected value from before was like A1 times P1 plus ... plus AN times PN. That's kind of what's going on right here. Here are my possible outcomes. X can maybe represent those. This is not like the total mathematical way of explaining this, but X are maybe my possible outcomes, and then F is kind of my probability of that outcome occurring. And then I'm going to grab all those possibilities between A and B. That's what the integral does for us. Okay, so there was my expected value. And then the variance in this definition, which you saw, is also what we saw before, but we're going to develop the definition that they give you at the end of the section also for variance. Whoops. So big A to B, and remember variance is just the difference between our possible values and the mean. Expected value is the same thing as the mean. Quantity squared, and then of course times the probability that that's going to happen, or the relative frequency that that's going to happen. All right. Okay, well, let's do an example as usual. Okay, so here's my example. So the life expectancy, that sounds pretty morbid, but we're talking about light bulbs, so it'll be okay. Expectancy, sound it out, Sarah. We'll say in hours. Okay. For a particular brand of light bulb, I'm not going to put particular. So for some brand of light bulb, is a continuous random variable. Now I'm being really lazy. It's a continuous random variable with probability density function. So again, lazy here, PDF, probability density function, f of x equals 0.01 minus 1 over 20,000 x, okay, for x between 0 and 200. Remember then, so what does x stand for? X stands for the hours. That's my life expectancy. This is my probability density function. So between, what is this really saying? The life expectancy, the minimum is 0. Well, that'd be a bummer of a light bulb. And the maximum is 200 hours. Okay, so part A here, what is the average life expectancy expectancy of one of the bulbs. So really what this is asking here is this is just asking what is the expected value, right? If I grab, remember what expected value is, if I grab a bulb at random, what is the expected value of its life expectancy? That's what this is asking. So I just plug this in. So my expected value is going to be from 0 to 200, right? X times my probability density function, which is 0.01 minus 1 over 20,000. We could change that to a decimal if we wanted to, dx. Okay, and because I'm running out of room here, I'm going to just do a little bit of work here to simplify. I'm going to go ahead and take that x through. So I have this. So now, you know, a lot of times when we get this high in calculus, the integral that we actually have to evaluate usually isn't too bad. It's really just setting it up. So I'm going to take the antiderivative of this guy right here, and I have my calculator to make sure I don't trust myself with arithmetic with no one watching me. So add 1 divided by 2, I get 0.005 x squared minus, so if I add 1, okay, I can do this. Add 1 and divide by 3, I get 3 times 20,000 is definitely 60,000, right? I'm pretty sure it is, from 0 to 200. So you can see that this actually isn't too bad. So I'm going to plug in the 200. I'm going to make sure when I plug in the 0, it really does go to 0. I've got to be a little bit careful about that, especially if E is involved. I've seen a couple of you, and this is an easy mistake to make, just not even worry about the 0. Sometimes it matters. And then we'll just plug this in. So 0.005 times 200 squared minus 200 cubed. And I'm going to put in some parentheses. I don't really need them, but just in case, divided by 60,000. All right. Let's see here. So this is great. Perfect. So what do I get? I get 66.6 repeating. So that's basically 66 and 2/3. So what does this mean? So remember in chapter, and I paused for a moment because just in my mind I was thinking we needed a probability, which we don't. This is expected value, right? So if I look at the 66.2/3, what this means is if I grab a bulb at random, the expected value of its life expectancy would be 66, basically 0.7 hours. Okay, I hope that makes sense. So let's go on. I have one more part to this problem. So the part B for this is, what is the probability now? Now we're getting to the question I had in my mind. What is the probability a bulb selected at random will last longer than average? So this is going to be, now I'm going to give you all these formulas on the test, but you're going to need to know when to use them. So we're asking for probability now. So basically I'm asking for, if I select a bulb at random, what is the probability, and we'll just round our answer, that X, right, the life expectancy of that bulb will last longer than average, so is greater than the 66.67. So now what we're doing, we're not doing expected value, we're doing probability density function. So I want to know, when is it greater? Well, what's the maximum life expectancy? 200. So I want to know, when is it greater than, lasts longer than average, right? There's average. There's the highest I can do. And what am I going to actually integrate here? I'm going to just integrate my probability density function. Not going to multiply it by X. Not going to multiply it by X because I don't want the expected value. So take the antiderivative. I hope that makes sense. Okay. So there's a difference between finding expected value and finding the probability of something happening. So make sure you understand when you're going to be using that, especially for the exam. And if I plug this in, I'll just go ahead and do this. Although I imagine some of you don't trust me, especially after some of my lectures lately. So 200 squared divided by 40,000. And then I'm going to put this all in my calculator. I'm going to put a parenthesis, 0.01 times 66.67. and then minus 66.67 squared divided by 40,000. Aren't you glad you were born in an era where we have calculators? So this number to me makes sense, right? Because we're talking about probability. We're not talking about life expectancy now of the light bulb. So what is the probability? Make sure you can answer these questions in a sentence. So I'm not going to because I'm lazy. I can be because I'm a teacher. Do as I say, not as I do, right? And so now I know, what does that 44.44% mean? That means if I select a bulb at random, the probability that it'll last longer than average is 44.44%. Okay, so I think that's pretty straightforward. Okay, so what I want to do now is I just want to show you on the last page, so we haven't done anything with variance, and the reason I haven't done anything with variance yet is because that equation that they gave us for variance is quite complicated. So what we want to do is we want to see if we can make variance a little bit less complicated. So what I'm going to do is I'm going to rewrite my expected value as the variable m for mean, okay? And what do I know? I know that this equals a to b x f of x dx. If f is my probability density function for a continuous random variable. Okay. So they do this all in the book, but let me walk you through it because I know algebra sometimes is the hardest part of calculus. So my variance then, if you go back in your notes and look at what my variance is, it's x minus my expected value, so I'll just call that m, quantity squared, times f of x. So what I'm hoping for is I'm hoping to find a formula for variance that'll be easier, because the problem with this right now is if I wanted to integrate this, I would probably have to square this guy, multiply it by the f of x, and then have multiple integrals, some which might involve integration by parts. So not that we don't love ourselves some integration by parts, but you know, I get that everyone is not like me. So let's, I'm going to FOIL this out. I'm going to take x minus m times x minus m. You can check my math. I think I'm going to do this guy right though. Okay, so I just wanted to FOIL that out really quick, and then we're going to see if we can find something that's going to be a little bit easier, okay? And then what I'm going to do here is I'm going to actually break this whole integral apart. So I'm going to distribute this f of x through to each term. Again, my goal here is to find an easier way to evaluate the variance. And I mean, there's going to be, because we're going through this. So, all right, so if I take this through, and then I'm also breaking up each term, okay? I'm breaking up each term through the integral. Now notice here, if I would have 2m x f of x, okay, so I just wanted to show you that because what I can actually do, and I didn't actually do it, is that 2m is a constant. It is not actually affected, right, by the integral because there's no x. So I'm just going to take the 2m out for that part right there. Still from a to b, I have x f of x dx. Okay, and then this is so cool. Then what my last one is, I'm going to do the same thing here with the m squared, and I'm just going to integrate from a to b f of x dx. I'm just going to put f dx because of room here. Now watch, this is so neat. I love this. This is so cool. I know, I should probably find a hobby or something, but look at what this is, people. Come on, people. What is this? X times f of x. That's just my expected value, right? Which we have called that to be m. So what I actually get right here is I just get 2m, and then this whole integral right here becomes m as well. So I just get 2m squared. And then this one, you guys are going to love this one. Okay, maybe not love it, but this, you guys, I'm integrating from a to b my probability density function. Remember, when I integrate a probability density function over the entire interval, it must equal 1. That's how it's even is a probability density function. So what I get right here is m squared. And so you see here, I have a much easier formula for variance now. I got a little too excited, so I don't have enough room. But here's my new formula for variance then, that is going to be much easier to use than the original formula. So if I take negative 2m squared plus m squared, I just get minus m squared. So this is a really useful formula. This is the formula I will give you on the test to calculate variance of a continuous random variable, because it's just easier. It's so much easier, okay? So another way to say that, I think your book uses the definition. So they do a little thing, definition, variance of x then equals the integral from a to b of x squared f of x dx, oh, I'm running out of room, minus basically your expected value or your mean quantity squared, okay? Pretty cool. I think that's just so cool. I just love how those integrals, the expected value comes up, and then the fact that we have a, probability density function comes up. That's so cool. All right, so find the variance of a continuous random variable x for a continuous random variable. Well, that's obvious. With the probability density function, I probably should put with. Problem is in my notes, sometimes I don't write things out. I just write little things and then I tell myself to remember that. So with the PDF, oh, I put 4 again. I meant with, but that's okay. With PDF, f of x equals 1 over 2 root x. And where is this a probability density function? Over what interval? From 1 to 4. So to find my variance, right, what do I need? Well, I know I need my absolute, or I need my expected value. So this is going to be from a to b, x squared times f of x minus my expected value squared. Okay. Well, to be able to calculate it, I need my expected value. So we have an extra step here to do. Okay, expected value is going to be from 1 to 4, x times my function, my PDF. Okay, so I'm going to simplify this a little bit. This is going to be from 1 to 4. If I kind of cancel, that's basically the 2 on the bottom, I'm going to just write as 1/2. And then if this is to the first power minus x to the 1/2, that gives me x to the positive 1/2 dx. And so what do I get here? I get 1/2 times 2/3, I believe, x to the 3/2 evaluated from 1 to 4. So if I cancel those 2's, basically get 1/3 times 4 to the 3/2, I square root the 4, it's 2. 2 cubed is 8. And then I'm going to subtract 1. So it looks like I get my expected value to be 7/3. Okay. Oh man, my work here. All right, so let's calculate variance and then we'll be done. This might be one of my shorter videos. We're going to be right at 20 minutes. That's amazing. So here we go. Here we go. Oh, I don't want any. All right, so I want to go from 1 to 4. X squared now times my probability density function. I see it. There's my squared. Are you yelling at the... And then I want to square my expected value. So if I square that, that's 49/9. Okay. So again, here I could even bring that 1/2 out if I wanted to. 1 to 4. This is x to the 1/2. X to the second minus, or 2 minus 1/2 is 3/2, right? If I get a common denominator. And then of course I have the minus 49/9. Remember, look at how my notation is good. So my notation, right? I'm not getting lazy. I'm bringing that 49/9. If I put an equal sign, you better mean it. So I have 1/2, take the antiderivative, 2/5 x to the 5/2 from 1 to 4. And then again, I have the 49/9. Okay, so I'm not being lazy here. All right, and now I'm gonna just do this on my calculator. So I'm gonna take 1 divided by 5, all times 4 to the 5/2, I believe is 32, but I'm gonna put it in my calculator just to make sure. I know 1 to the 5/2 is 1, and then I'm gonna subtract 49/9. And I get 34/45, or 0.76 basically, which is pretty small, right, for a variance, I would think. So that would say that my continuous random variables, that data is pretty close together. All right, you guys, I think that's it. I'm under 20 minutes, so I better stop talking. Let me know if you have any questions.